exponential functions. So first we'll define these. So if we let b be a constant real number such that b is greater than 0 and b is not equal to 1, then for any real number x, a function of the form f of x equals b to the x is called an exponential function of base b. Now, some common mistakes with this. The base of an exponential function must not be negative. So avoid situations function values are not real. And the base of an exponential function must not be equal to 1 because f of x equals 1 to the x is equal to 1 for all real numbers x. So let's look at an example. And let's start with, well, let's look at two examples. We'll look at f of x equals 5 to the x, and we'll look at g. Actually, let's use some of the abilities I have with this. And we'll go g of x equals 1/5 to the x. Okay, so let's draw our graph here. Then let's look at f of x. Okay, so let's just graph these functions. We'll let x equal 0. X is 0, f of x is 1. If f of x is -1, we get 1/5. And I don't think we're going to go beyond that. If x is 1, we're going to get 5. And if x is 2, we're going to get 25. So this is going to shoot up pretty fast. Okay, now let's switch to our other color. That's black. Is it? That, there it is. So g of x, if x is 0, it's going to be 1 as well. If x is 1, it's going to be 1/5. If x is -1, 1/5 to the -1 is 5th. Now here we're looking at this. So this is g of x. Okay, some important things to note about this. The graph of an exponential function defined by f of x equals b to the x, where b is greater than 0 and b does not equal 1, has the following properties. For b greater than 1, f is an increasing exponential function called an exponential growth model. Here we go, right here. F of x there. If 0 is less than b is less than 1, it's a decreasing exponential function, sometimes called exponential decay model. The domain is -infinity to infinity. This goes on forever. This goes on forever. All these two. The range, however, is 0 to infinity. It doesn't go negative at all. It never reaches 0. So thus we have a parentheses instead of a bracket. The line y equals 0 is a horizontal asymptote, and the function passes through the point 0, 1, because f of 0 equals b to the 0, which is 1. Okay. So let's look at g of x equals 2 to the x plus 2 minus 1. Let's see what happens here. So we may have to run some points here. Well, what if x is negative 2? Then we have 2 to the 0, which is 1, minus 1, so we get 0. What if x is negative 1? We have 2 to the 1 minus 1, which is 1. What is x is 0? We have 2 to the second, which is 4, minus 1, which is 3. If x is 1, we have 2 to the third minus 1, which is 7. And maybe we should go negative 3. Or 2 to the negative 1, which is 1/2 minus 1, or 1/2. So what am I looking at here? Negative 1, 2, 3. 1, 2, 3, 4, 5. Negative 3, we're at 1/2. Negative 2. Negative 3. We're at negative 1/2. Sorry. Negative 2, we're at 1. Or 0. Negative 1, we're at 1. 0, we're at 3. And 1, we're at 7. So this, if you remember from our translation, drops our asymptote down to negative 1 instead of the x-axis. Moves this over. Okay, so then there's some real world applications of this. The first one being simple and compound interest. So we're talking formulas relating to simple and compound interest. We have the principal amount, which is P. T is time in years. R is the interest rate in decimal form. N is the number of times compounded in a year. So we have our simple interest. Interest equals PRT. Compound interest, A equals P times 1 plus R over N to the NT. And we have our continuous interest, which is A equals P times E, the constant E, to the RT. So let's look at a couple examples of this. And we'll go with, suppose that $8,000 is invested. So our principal is $8,000. It pays 4.5% a year. So in decimal form at 0.045 with the following compounded. Let's just do one of these. We don't need to do a whole bunch. We're going to go with compounded monthly. So N equals 12. This is how this works. Total amount in the account after 5 years. That's what A is. So we have A equals our principal times 1 plus our rate, 0.045, divided by number of times. And I forgot T is 5 in this case. To the 12 times 5. So here I'm looking at 8,000 times 1. 0.045 divided by 12 plus 0.00375 to the 60th. I'm looking at 8,000 times 1.00375 to the 60th. Times 8,000 equals, and I get a final value of $10,014.37. Okay, we can also use these as decay models. So let's look at the half-life of radium is 226. Radium 226 is 1,620 years. In a sample originally having 1 gram of radium 226, the amount AT in grams of radium 226 present after T years is given by AT equals 1/2 T divided by 1, or 1,620, where T is the time in years after the start of the experiment. How much radium will be present after, and let's just go with 3,240 years. So A of 3,240 years is simply 1/2 times 3,240 divided by 1620, which is 1/2 to the 1/2, which is 1/4 gram. That's how those questions work. When you hear them talk about the half-life of things, carbon-14 dating is done that way as well. And that finishes up section 4.2. That'll be it for today, and I will see you next time.